Hello everyone. So let me here explain what is it that I'm doing with all these effects and processors. Well, they are, as I mentioned before, they are meant to be effects, but they are routed as processors, except they all have a mix slider so that you can decide how much of every single one you want to use. So the sound effect is going to be as an effect, not as a processor. But anyway, let me start speaking about the flanger and chorus effects first. They both are very similar. The way they work is that you have a clean signal. I have my guitar plugged in right now. So this is a clean signal of the guitar. And what these two are going to do is that they are going to create a copy of the signal, and then they are going to delay that copy of the signal, but that delayed version is going to fluctuate its delay time. It's going to fluctuate that delay time periodically. So like a sine wave, for instance. So the delay time will go up to a certain amount and down to a certain amount. And what that's going to generate is some change in pitch too. So as the delay time fluctuates, the pitch fluctuates as well. So creating like kind of a vibrato, but this vibrato is also delayed in time. So what happens is that when you combine the dry signal with that one which has been delayed and that has this little vibrato, then you're going to get the flanger or chorus effects. The difference between the two really is just how much are we delaying the signal, or how much the delay time is fluctuating. So on the flanger, I decided to use from 5 to 10 milliseconds. So it draws a sine wave that goes in the minimum of 5 milliseconds and the maximum of 10 milliseconds, whereas the chorus is from 25 milliseconds to 30 milliseconds. So it's still 5 milliseconds difference between the two, but the first one is between 5 and 10, and the second one is between 25 and 30. And that's going to create a different sonic effect. So that's why they have different names and they have a distinct sound. So what you control here, well, I already talked about the mix, is just how much of the delayed signal I'm mixing with the original clean signal. Now, there always needs to be an original clean signal. So really this mix doesn't go to 100%. It goes to maximum of 50% because I still need all that other 50% for the clean signal so that they can interact together. Then these depth parameters are just telling it for the flanger, for instance, it's going from, I already told you that it went from 5 to 10 milliseconds, but that's at its maximum. So where it is right now, you could say that it's from 5 to, let's say, 7.5 milliseconds. So that this is the minimum will be from 5 to 5 milliseconds, so no fluctuation at all, only the delay. And then here it'll be from 5 to 10 milliseconds. So you kind of can control that amount of delay. The same thing from here. So from here it will be from 25 to 25, so no fluctuation. And then this will be from 25 to 30 milliseconds fluctuation. Then the rate is just the frequency of that oscillation. So I decided on some specific frequencies that I experimented with and realized that I liked the sound of them. Of course, these frequencies need to be under 20 hertz. Those need to be low frequency oscillators, because if you put rates that are higher than 20 hertz, then you're not going to hear this effect anymore. You will have a different type of effect. So I don't remember specifically which frequencies I decided them as maximum, but it's somewhere in here in the control specs. Maybe we can check here real quick on the chorus rate control spec. Is a minimum frequency of 0.01 hertz, so very close to 0 hertz, and maximum frequency of 2 hertz. That's with the rate all the way up. Okay, so that's how those work. Let me show you how they sound like. So again, this is the dry signal. And then if I start adding some flanger, this is how it's going to sound like. see that effect? That's just the oscillation of the delay plus vibrato interacting with the dry signal. And then here's the chorus. It's a slightly different effect. It's similar really, but it has some differences in the way it sounds. So there are those two. Now, something that I implemented here is that, let me go to the scene def real quick. Where is it? This is the GUI. Here's the scene def. So as I described earlier, let me show you here this little picture. This will be like only having one delayed signal, right? Following that sine oscillator. But the problem with that is that you can kind of hear this wave here being out of tune, and it's a little unpleasant. So then I tried using two delayed signals that were 180 degrees out of phase. So it will look like this, just duplicating the two. So while this one is going up in pitch, this one was going down in pitch, and hopefully that could disguise the fact that it was out of tune a little bit. But then the problem with this is that you see these notches right here whenever you add the two signals together. And so it started having like kind of a tremolo effect. So in order to compensate for that, I created a third one, and instead of displacing them by 180 degrees, I displaced all three of them by 120 degrees. So really I have three sine oscillators that are 120 degrees apart. So the notches are a little smaller, so you kind of not hear that tremolo effect, and you also don't hear the detuning that happened if you already had one. So here on my scene def, you can see that I have LFO1, LFO2, and LFO3. So those are the ones that are controlling each one of the delays. So it sounds richer, and it sounds, let me show you here. It sounds kind of fuller than if it had only one or two delays. So I experimented with that, and I realized that I wanted to do a tri-phase, meaning that I have three signals and they are a third of the circle out of phase. So that's 120 degrees. All right, you can even combine the two, and then you get an effect like this. And there it is. All right, now let me go to the Octaver. This is a peculiar effect because the way that it works here on our digital systems is that SuperCollider or the whole system really needs to take the signal that is coming in and take some time to analyze it so that it can move it an octave lower and an octave higher, which is the two ways that it's operating here. So it can't really do it in real time. It needs a little bit of a buffer time in order to make those calculations, because it cannot have the effect happen like in the present, because it doesn't really know what's coming in. As Dr. Thompson says, these things cannot modify the future. They can only modify the past. So the longer that buffer time is, the more accurate the calculation is to raise it an octave higher, or to bring it down an octave for the low octave. So it's kind of a compromise there. The lower the buffer time, the less accurate the calculation, and it doesn't sound quite as good. But if I give it a little more buffer time, it sounds better, but it's delayed. So I kind of experimented with those window times to figure out which one sounded the best. So if the way this works is, of course, I can mix the signals, but if I put it as a full mix, 100% wet, and only the low octave, it's kind of an electric bass, right? It just goes an octave lower, and I can do the opposite with the octave higher. But it does have a latency, so you have to kind of be aware of that, and maybe you can combine these two a little bit and sound like this. Or if you don't want any dry signal at all, you can combine the two, so you have those parameters there. All right, and then finally you have the delay, which we all know how it works. but I incorporated a feedback loop into that delay. So not only you have the mix and the delay time that you want to accommodate, but also how much of the delay signal is coming back into the delay effect so that you have more repetitions. And the minimum value is going to be 0, so just hearing one repetition, right? That's the minimum value with only one repetition, so no feedback. The feedback factor here is 0. But then if I move it all the way up, you'll have a lot of repetitions. It keeps going for a long time. And actually, if we're talking in percentage times, this will be 90%. I didn't put it 100% because if I set this as 100%, then you will keep repeating forever. And that's kind of inconvenient. So I put it at a maximum of 90%, which is still a really long time for it to keep going with repetitions. You see that the drop in signal power is very small every time. So it takes a long time. So I don't think I will ever use it like that. I'd rather put it like somewhere in here. And of course you can play with these parameters. So you get like effects like these. Etc. All right, so this is the project that I created. The idea with this is not to leave it just here. I would like to create more effects in the future. Of course, this is not just about learning how to code them, but also learning like what's the mathematical functions that represent what each one of these things do, like as I explained with these sine waves and all that for the flanger and the chorus. But of course, there's more effects and they can be created in more complex ways. So I'd just like to keep this as a file that I can keep adding to and use it just as an experimentation tool. And right now I have it plugged into my guitar, but it can also take any other type of line signal or microphone signal, so you can modify anything that you want, really, even a buffer, although you will have to route it through an actual feed to the interface if you wanted to do that. But yeah, that's my project. If anyone happens to want to play with it, I'll be happy to send you the file and you can just hook it up and play with it. And then also all the controls are mapped to my MIDI keyboard, and you can modify them in real time from the MIDI keyboard. All right, thank you.